Welcome back. In this video, we're going to compute the following integral using two ways. So the first one is that we know that the derivative of the exponential is itself. The antiderivative of the exponential is itself. So we know exactly this one is, so it's e to the power x between 0 and 1, which is e to 1 minus e to 0, which is 1. So we know this one. This is the value of the integral. So now we're going to use the left Riemann sum in this first video. And after that, if we have time, we're going to use the right Riemann sum. Okay? So let's first get an idea of this function. So we know the so here, so this function is continuous because it's here, the exponential is continuous, and we want to compute this one between 0 and 1. Okay? So this is 1, this is e to the power 1, 1x is 0, it's 1. So when I use the left Riemann sums, okay? The left Riemann sum. So defined as a subdivision x sub k, which equals a plus k b minus a over n. In our case, we know that b is 1 and a is 0. So we have a is 0, b is 1, a is 0. So we have k over n. Okay? So let's get a big picture. Okay? So let's assume that this is xk and this is xk plus 1. So the left Riemann sum computes these ones. Okay, let's add one more here. So it's computing, this function is increasing under the graph. So we are missing some values. But as n gets bigger, we get closer to the true value, and we're going to find it exactly. So we are using the left Riemann sum. Okay, so how can we express this one? Let's call this sum the Riemann, let's call it R, and the sum is defined as, let's say, the limit as n goes to infinity, okay, for k between 0 and n minus 1 of 1 over n, which is delta sub k, delta sub n. How many subdivision here? Delta sub k. So we have n division, and we are taking 1 over n. So this is 1 over n, okay, times f of xk. We know our f here, okay. So delta k here, it's the difference between two. Let's compute it, in fact. So we have delta k, or delta n, so it's xk plus 1 minus xk. Okay, in our case, we have xk is k over n, so we have k plus 1 over n minus k over n, and when we do that, we get 1 over n. Okay, so we have 1 over n here because delta n, so like, let's say it's some books here is delta k, some delta n, but let's say delta, or sometimes it's good to call it delta x. It's 1 over n. This is my favorite. Delta x is 1 over n. Okay, because that's what we get when we switch to the integral. We get dx. So for me, let's call it delta x. So we want to compute this one, but let's simplify it more. So we have r as, let's go back here, we have r is the limit as n goes to infinity of 1 over n. So we have f of xk, and xk is k over n. And what's f? F is e to the power x. So we have e to the power k over n. Okay? So this is the limit. Okay? So I forgot the sum. So k going from 0 to n minus 1, because we are taking the left sums. Okay, let me write it one more time here. So r is the limit as n goes to infinity of 1 over n, the sum k from 0 to n minus 1 of e to k over n. Okay, now we have our formula. Okay, so here let's rewrite this one. Okay, let's forget about 1 over n and forget about the limit. Let's forget about this one. So let's just focus about this one. So the sum, okay, let me, k from 0 to n minus 1 of e to k, or e to n, e to 1 over n to the k. So it's the sum k from 0 to n minus 1, e to 1 over n, everything to the power k. So this is a geometric sequence with the ratio, or the base, is 1 over n. So what we get, it's like the first term, which is 0, minus the last one, which is 1 over n to the power of n minus 1 plus 1, which is 1. So it's 1 minus e over 1 minus e to 1 over n. So this is this sum here. So this is its value. Okay, let's go back here and see the limit. So now let's take the limit. So limit of this sum. So the limit, so this is r 1 over n, 1 minus e over 1 minus e to 1 over n. So let's take 1 minus e to the front, because it doesn't depend on n. So we have 1 minus e, the limit 1 over n times 1 over 1 minus e to the power n, as n goes to infinity. Okay, so here, what's this limit? Okay, the limit of 1 over n when n goes to infinity is 0. This one, e to 1n, when n goes to infinity, it's 0, but 1 minus e to the power 0 is 1, so we have an indeterminate form. Okay, so how can we solve this one? Okay, how can we find this limit? Let me do more work here and we see what we can do with this. So our limit, let me write it down. Our r, in fact, is the limit as n goes to infinity of 1 minus e over n times 1 e to 1 over n. Okay, we said we can move the limit outside, the 1 minus e outside, and we need to find this limit here, 1 over n, 1 minus e to the power n. Okay, so this is the limit that we are interested in. So here we have a sequence, okay? But a sequence is a function, and it's a particular case of a sequence of a function. So let's define the following function: f of x, 1 over x times 1 minus e to 1 over x. So let's assume that x is positive, because we are interested in the limit as x goes to infinity. Okay, so we are interested in this limit. So 1 over x, 1 minus e to 1x. If we can find this limit, it's the same as the limit for the sequence. But let's make it more easier. So let's use the change of variable. Let's put 1 over x equals u. So as x goes to infinity, u goes to 0 from the right. So we have the limit as x goes to 0 of 1 over, okay, so 1 over x is u over 1 minus e to the power u. Okay? Now again, when we plug the values, we get 0 over 1 minus 1, which is 0. So we have to do more extra work. But we know Tylor series. We are close to 0. So we can use the Tylor series. So e to the power e is 1 plus u plus some u squared, but we are not interested in. So taking e to the power u minus 1 is equal u plus u squared plus plus. So here, if we divide, this one is never 0. So if we divide, we get 1 over u over e to the u minus 1 plus u squared. So we're interested in this part. So what's the limit? Okay, and this one is going to be 1, but we are interested in 1 minus this one. So this limit is minus 1. Okay, our limit here is minus 1. So from here, because we are interested in 1 minus e to the power e, not e to the power u minus 1. So it's minus 1. And we plug it here in r, we get e to minus 1. And that's what we get when we first did the regular ways without using the left Riemann sums. What about the right Riemann sum? What can we get? Can you try it?